All right, welcome. Today, we're going to crack open one of the most fundamental ideas in computer science, the linear search algorithm. It's simple, it's direct, and you know what? It's surprisingly powerful. Let's dive right in.
Okay, so picture this. You're looking for a specific book, but it's on a bookshelf that's a complete disaster. Nothing is sorted. What's your gut instinct? You'd probably just start at one end and look at every single book one by one until you find it, right? Well, that right there is the core idea we're talking about today.
In the programming world, that whole start at the beginning and check everything method has an official name, linear search. It really is the most basic way to find something. No fancy tricks, no clever shortcuts, just a straightforward, sequential check from start to finish. So here's what we've got on tap for this explainer. We'll kick things off with why it's so simple. Then we'll walk through exactly how it works. After that, we'll look at some actual C code. We'll analyze its performance. Is it fast or slow? And finally, we'll figure out when you'd actually want to use it. First up, why we call it the simplest search. You know, what's so cool about the linear search is that it feels so familiar. It's pretty much how we solve a lot of real-world problems, just by being methodical and checking all our options. And that's really the whole shebang. You have a list, you have something you're looking for, so you just start at the beginning, you check each item, one after another, until you either get a match or you run out of things to check. In a way, it's an algorithm you've been using your whole life. Okay, so how do we take that simple idea and turn it into a formal set of instructions that a computer can actually follow? Let's break it down into a real algorithm. So here's the game plan. You start at the very first spot, index 0. You ask, is this what I'm looking for? If the answer is yes, awesome. We stop right there and report back the position. If it's no, we just move on to the next spot and ask the same question again. And we keep doing that over and over until we either find it or we get to the end of the list. If we get all the way to the end with no match, well, then we know the item just isn't in our list. Let's make this real and see it in action. We've got a simple array here with 5 numbers in it. Our mission is to find the number 30. Let's trace how the algorithm would do it. Okay, the algorithm starts at the very beginning. It looks at the first number, 10, and it asks, are you 30? The answer is nope, so it moves on. Now we're at the second position. The number here is 50. The algorithm asks again, are you 30? Still no, so the search has to continue. And then we get to the third spot. We find the number 30. The algorithm does its comparison, and ding, 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 it's a match. The search stops immediately, and it reports back that we found our number at position 3. Notice, it doesn't even bother looking at the 70 or the 80. Job done. So that all makes sense in theory, right? But what does this actually look like when we turn it into code? Let's take a look at how we'd write a C program to do exactly what we just walked through. So here we have a really simple C function that does a linear search. Let's break it down. It takes in 3 things: the array itself, AR, the size of the array, N, and the number we're looking for, X. Then we hit this for loop. It starts a counter, I, at 0, and just goes up one by one. And inside that loop is the real magic, that if statement. It checks if the current element of the array, ARI, is equal to our target, X. If it is, boom, we return I, which is the position where we found it. And if the loop gets all the way to the end without finding a match, then it returns -1, which is our signal that the number isn't in the array. So we know it's simple. We know it works. But is it any good? Which brings us to the big question with any algorithm. How fast is it really? Is linear search a sprinter or something a little slower? In computer science, we use this thing called time complexity to measure an algorithm's speed, and we usually write it in big O notation. As you can see, there are 3 scenarios here. The best case is O of 1, which we call constant time. That means it's super fast. But the average and worst cases are O of n, or linear time. That n stands for the number of items in the list. So what this means is that the search time grows directly with the size of the list. Let's break that down. Think about the best possible luck you could have. The item you're looking for is the very first one you check. One look, and you're done. That's O of 1. Now, what's the worst luck? The item is at the very, very end of the list. Or even worse, it's not in the list at all. In that case, you have to check every single element. If your list has n items, that means you have to do n checks. And this really gets us to the core trade-offs. On the plus side, it's incredibly simple to understand and write the code for. And this is a big one. It works on data that's completely disorganized. But the downside is just as obvious. If you have a massive list, say 1,000,000 items, this thing can be painfully slow because it might just have to check all 1,000,000 of them. So you might be thinking, if it can be so slow, why on earth would a programmer ever choose to use a linear search? It's a really good question. Well, it all comes down to using the right tool for the right job. Linear search is actually the perfect choice in a few key situations. First, if your list is small, who cares if it's not the absolute fastest? The simplicity wins. Second, and this is a biggie, when your data is a total mess and isn't sorted, faster algorithms like binary search won't even work. And finally, sometimes you just need a solution now, and the time you save by writing simple code is more important than the milliseconds you'd save at runtime. I think this quote just nails it. Don't think of linear search as a high-performance race car. Think of it more like a trusty old pickup truck. It's not going to win any races, but it's reliable, it's simple, and it'll get you where you need to go, especially when the road is bumpy and messy.
So I want to leave you with this thought. We live in a world that is obsessed with speed and optimization. But as linear search shows us, sometimes the most powerful and elegant solution is actually the simplest one. It's a trade-off we see everywhere in technology. So when is good enough not just good enough, but actually better?